Okay, so today we are going to look at item 4, that is section B. So this section B is comprising of heat and mechanics. And under heat, we have a number of topics, where we have heat quantities and vapors, we have heat transfer, we have temperature measurement. All those fall under what? Under heat. Then mechanics. We have topics like linear motion, we have work, energy, and power, we have turn effect of forces, we have machines. All that work is under this what? This section, part 1 of section B. So today I want us to go through this item together, item 4, and we understand people will be having questions. They will be asking questions. People who need guidance on some responses, uh, they will get the answers in today's presentation, mainly focusing on what we are doing right now. So item 4 goes by saying, the organizers of the bicycle racing competitions have set a distance of 5,000 meters and an average speed of 10 meters per second as the minimum standard for the participation in the final competitions. During the training session, a certain racing cyclist's journey is in 3 stages. Stage 1, the cyclist accelerates uniformly from rest to 12 meters per second in 20 seconds. Stage 2, the cyclist cycles at 12 meters per second for a distance of 4,800 meters. Stage 3, the cyclist decelerates uniformly to rest. The whole journey takes the cyclist 500 seconds. That is the total time for the journey. After training, the cyclist must present the training motion on a speed time graph for quick analysis and determination about whether the cyclist will participate in the finals. The cyclist is also bothered by too much heat in the rims of the bicycle and was advised to always cool the rims in water every after stopping. The cyclist needs to understand whether the material of the rim will not burn the tire during the braking session and why not other liquids for cooling the rims. Then we have heat capacity of the material of the tires is 210 joules, 10 joules per Kelvin. The temperature just before braking is 48 degrees Celsius. Mass of the cyclist is 65 kg, ignore the mass of the bicycle. Then 20% of the work done during the braking is converted to heat energy in the limbs and is also absorbed by the tires. The limb may burn the tire if the temperature of the tire increases beyond 62 degrees Celsius. That is our item. So we go under task. As a student of physics, help the cyclist to come up with the motion graph and determine whether he will participate in the finals. That is part A of the task. Then part B, understand the source of heat in the rims and why water is the best for cooling the bicycle after braking. And the last part, determine whether the rim material will not burn the tires. So I think all of us, we have seen the what? The question, the item. Now I want us to start by breaking it down and starting to respond to this item. And sure you are able to see my screen. If yes, please, you can notify me that you are able to see the screen. Are you able to see the screen? Are you able to see my screen? That's good. People are able to see my screen. Now, I want us to start now answering this item. Now, basically, when you're responding to items in the competence-based curriculum, mainly we follow three things. The first one is always identification. So we begin by identifying the problem. Then we go ahead and explain that problem and maybe the solution to that problem. Then we also come and give a conclusion. That's how we respond. You begin by identifying. After identifying, you explain. Hmm? You explain. After explaining, then you come and give us a conclusion. So let us begin with the first part here of the task, which says, come up with the motion graph and determine whether we will participate in the finals. They want us to come up with the motion graph and determine whether this person will be able to participate in the finals. But we go back to the conditions. The conditions for someone to participate in the finals is that this person must cover a distance of 5,000 meters and must have an average speed of minimum of 10 meters per second. Those are the conditions for someone to participate in the finals. So as you're doing the item, you need to go back and be looking at the scenario that what do they want? What are the conditions from the what? From the scenario. Then let us by analyzing this. The first stage is saying the cyclist accelerates uniformly from rest to 12 meters per second in 20 seconds. Then the second stage, the cyclist cycles at 12 meters per second for a distance of 4,800 meters. That's the distance covered. But now this person, the second stage here, the person is moving with a constant velocity. Then in the third stage, they are saying the cyclist decelerates uniformly to rest. And lastly, the whole training journey takes the cyclist 500 seconds. Now, our first part is going to be analyzing the stages here. Analyzing the stages. Now, analyzing the stages, we are going to come and go to display. I'm going to display a plane. A plane page here so that we can be able to do what? Hope, are you able to see my screen? So now the first stage, the person starts from rest. The person starts from rest in the first stage. So stage one, our initial velocity u is 0 meters per second. Then our final velocity is 12 meters per second. Then our time was given as 20 seconds. That is stage one. Then we can come and find acceleration here. Then we come to stage two. Stage two, our initial velocity is 12 meters, and still our final velocity will be 12 meters because in stage two, they are saying that the person was moving with a constant velocity and the time is not known. Time is not known. But now the distance that was covered in this stage here is given as 4,800 meters. That is the total distance that was covered. That is the total distance that was covered. Now, that is the second stage. So you can come and find the time here, whereby time here is going to be given by our time. Since the body is moving with the constant velocity, our time is going to be given by s divided by velocity. So our time is going to be 4,800 divided by our velocity, which is 12, and we are coming up with 400 seconds. So that is the time that was taken when this person was moving with a constant speed. Then stage three. Now remember, when you are doing this analysis here, the final stage for the previous stage becomes the initial for the new stage, for the new stage. So now for this case here, in stage 3, our initial velocity now u will be 12 meters per second. And then our final velocity, because here the body came to rest, the cycles came to rest, our final velocity is going to be 0 meters per second. And then time here is not what? Is not known. But you can come and find a time, whereby our time in this region here, total time was 500 seconds. So it will be 500 seconds minus time in the first stage, then minus time in the second stage, which will give us our time as 80 seconds. Then we can come and find the acceleration here. V is equal to u plus at. Our v is 0 and our u is 12 plus a times our time, which is 80. Then I'll have my a is going to go to minus 12 divided by 80. And a is simply minus 0.15 meters per second squared. That is the retardation. Now, here, our acceleration still can be got by using the first equation of motion, whereby my v is 12, my u is 0, my a, I don't know it, and my time is 20. My 12 is going to go to 20 what? 20a. Divide by 20, and the a is going to equal to, when you get a calculator, a is going to equal to 12 divided by 20, 12 divided by 20, which gives me 0 point what? Which gives me 0.6, 0.6 meters per second squared. That is our analysis. Before even coming up with our velocity time graph, this is our analysis. Now from here, we shall come and put this on the velocity time graph or on the speed time graph. If you have any question in the inbox, please, I'm going to be, in case you have any question, you can ask before I go to the next stage. In case you have any question, you raise up the hand and then you ask before you can proceed. So currently, I'm not seeing anybody asking. That means we are the same page. I'm seeing Komakech. I'm seeing Fresh here. You can talk.
Good afternoon, teacher.
Good afternoon to you.
Teacher, you talked about on stage 2, you were saying that the answer is the initial to stage 3.
Yeah.
And
Now, when we
I
are
wanted
analyzing this
to
motion graph,
inquire, like, how can we use that knowledge in other scenarios?
Now, let me just, we are analyzing. When you are analyzing velocity time graphs, see, or maybe questions involving in linear motion, what you do, the final velocity for the previous stage becomes the initial velocity for the new stage. Now, if you observe on my screen, in the first stage, our initial velocity was 0 meters per second because the body was from rest. And our final velocity was 12 meters per second, not so? Now, when you come on the second stage now, our initial velocity will be the final velocity in the first stage. That's why in our second stage, our u is 12 meters per second. Am I clear? Okay, we can proceed. Then if you look in the third stage here, they just told that the cyclist decelerates uniformly to rest. They never gave us the final velocity. They never gave us the initial velocity. So now what you do, the final velocity in the previous stage, that was stage 2, was 12 meters per second. That one will obviously become the initial velocity in the third stage. That's why in my third stage, my initial velocity is 12 meters per second. And because the body has gone to rest, now our final velocity will be 0. So when analyzing, the final velocity for one stage becomes the initial for the next stage. That helps you to analyze in the process of analyzing, identifying the velocity in each of the stages. Okay, now let us look at the velocity time graph here. Now, velocity time graph here, in the first stage, we have uniform acceleration. So we shall come up with our graph. Now, what happens here, in most cases, velocity time graph questions, they don't need you to come up with a graph paper. I'm seeing a hand. Sharifa. Sharifa, you can ask or you can say something.
Teacher, teacher, the
Yes.
question. The question. Relax the question.
I'm saying what?
The question.
The question, maybe you came in late because we had to first go through the what? The question, but let me first take you back to the question. Uh, uh-huh. Now, the question is here, on this task here, they are saying, as a student of physics, the cycle is to come up with the motion graph and determine whether we will participate in the finals. And determine whether we will participate in the finals. That's what we are answering. Someone has a question? Yes, you
Sir,
can ask.
good afternoon. So I'm asking that, can you please
Good
repeat?
afternoon to you.
I'm asking if you can please repeat the stages. Some of us have just joined and we are not like understanding the way you did the stages, like stage 1, stage 2, stage 3.
Oh, okay.
I guess teacher, we're not around some of us. So the question. We're just reaching
Oh,
that. Yes, teacher, about the question only.
you came in late. Okay, we shall go
Then
back.
even then teacher on the things of initial velocity and you said to continue with the what? The last velocity should be the initial for the second stage.
The final for the previous stage becomes the initial for the new stage now.
Oh yes. Okay.
We are going to come back on that. Yes. Seeing Komoni, the hand is up. Okay, let us proceed. Let us first go through this question here. Yes, Komoni.
Sir,
Yes.
when it comes to such kind of questions, are we not
Mm.
going to define the key terms first before we proceed with the calculations?
The key terms.
Yeah.
And no, we may not define the key terms because we are looking at the task now. What is the task asking us?
Okay.
Yeah, what is the task asking us? We don't need to define the key terms.
Mm.
What I've been doing here, I have been first, that is just called an analysis before I can
Okay.
come up with a velocity time graph.
Mm.
So in the process of you responding to this item here, you don't need to define the key terms because they are not part of our task.
Okay.
Okay. Now our task is here. This is our question. People have just joined. Item 4 is saying the organizers of bicycle racing competitions have set a distance of 4,000 meters and an average speed of 10 meters per second as the minimum standard for participation in the final competitions. During the training session, a certain racing cyclist's journey is in 3 stages. The stages are given here. The cyclist accelerates uniformly from less to 12 meters per second in 20 seconds. Stage 2, the cyclist cycles at 12 meters per second for a distance of 4,800 meters. And stage 3, the cyclist decelerates uniformly to rest. Then lastly, they are saying the whole training journey takes the cyclist 500 seconds. Now we come on our task. On the task, they are saying, as a student of physics, help the cyclist to come up with the motion graph and determine whether we will participate in the finals. That's what we are doing. People just came in late. Now, the first step here is we have done our analysis here. This is our analysis. We have done our analysis here. So our analysis, stage 1, the person began from rest and then had a uniform acceleration to a velocity of 12 meters per second in 20 seconds. We can find acceleration there. We have come up with it using the first equation as 0.6 meters per second squared. Then you see that our initial velocity in the first stage was 0, final was 12. Now, when you come in the second stage here, our initial will become the final here. So our final here was 12, then our initial here is going to become 12. And because here the person maintained the velocity, what does it mean? That the final and the initial, they will be the same. They'll be the same. But they gave us the distance that was covered in stage 2, which is 4,800 meters. So you can use this distance here and the velocity to come up with time taken when this person is moving with constant velocity. And we have come up with our time as 400 seconds. That is in the second stage. Now, in the third stage here, our final velocity was in the initial velocity, in the second stage, our final velocity was 12. So our initial will become 12 meters per second. Then the final will become 0 because this person here, the bicycle was brought to rest. So the final velocity will be 0. Time is not given. But because they told us that the total time that was taken in the journey was 500 seconds, so you can say 500 minus the time for the first journey minus the time for the second journey, the time that will be left there, it will be the time for the last stage, and we have come up with our time as 800 seconds. Using the first equation of motion, we are coming up with our A as minus 0.15 meters per second. That is the analysis of the three stages. Now let us come up with the velocity time graph. Now, when you are coming up with the velocity time graph, it is not a must that you must put it on a graph paper. This is like a sketch of the motion of this bicycle. But you must be accurate in terms of coming up with a triangle. They must be straight line. So now we shall come and draw our vertical line. Then we do our horizontal line. Now you put the arrow here, and here we shall be having velocity in meters per second. Then here we shall be having time in seconds. That will be the time. Now remember, in the first stage we are having uniform acceleration. And uniform acceleration, it is always a slanting line going upwards. So we shall start from 0, and it was from 0. So it will be a straight line. And here our velocity was attained is going to be 12. So the corresponding time here, you simply come up with a dotted line, and we are putting 20 because that is the corresponding time. Now, the second stage here, we are having constant velocity, which is supposed to be a straight line because time is increasing, but velocity is not changing. So we shall have this on here, and this thing is cumulative. So 20, it was for the first stage, but time for the second stage is 400 seconds. So plus 400 here, we shall come up with 420. That is our time for the two stages. Now, in the third stage, we are having uniform deceleration, which will be going downwards because velocity is what? Velocity is reducing. In how many seconds? In 80 seconds. So we shall have 420 plus 80, which will give us 5 what? 500. Time that is supposed to be here is supposed to be the total time. So this is going to be our velocity time graph or our motion graph. So here we have area 1 for the first stage. We have area 2 for the second stage. We have area 3 for the last stage. I'm welcoming any question before I can proceed. I am seeing it. Mali.
So don't we need to put the title on this graph?
The title?
Yes.
We can put the title, we say a velocity time graph for the motion of the cyclist. Thank you so much for that correction. You can put it. Though, for this case, when you are marking, it does not carry any what? It does not carry any mark when you are marking. So you simply say a velocity time graph for the motion of the cyclist, but it won't be getting any mark.
Talked about the markings of the graph. You need to put
The
them
what?
also.
The what?
The other markings on the line, on the vertical line and horizontal line.
Other markings? Other
Yes.
markings are not needed. The other markings are not needed here. Even if you don't put them
Okay.
there. Are you getting it? Like Smayanga
Yes.
from then 20, what and what. As long as you can capture the velocities, the initial, the finals in each and every stage on the vertical axis, you can ignore that.
Yes.
Yeah.
Okay.
But what is very important here, please don't forget to label the axis. That the vertical axis, it is velocity in meters per second. Horizontal, it is time in seconds. Don't forget that because it carries a mark. Yes, Margaret.
Good afternoon, Master.
Good afternoon to you.
I was trying to ask that these SI units, are they standard? For example, in a certain mock paper, they used meters per hour. Had we had to change this to meters per second, or it was
No. You finish up.
or it was free to use how they gave it to us when we are doing this sketch?
Now, things involving in the units that are given to you in the question and what you put on the velocity time graph here,
Yes.
Now, if you have your velocity in meters per second, it
Yes.
is a must change the time to seconds. It is a must. If the velocity is in meters per second, please change the time to seconds also. Even if they have given it to you in hours, convert that time to seconds. So that we have meters per second, and then we shall be having seconds on the horizontal axis. If you are given kilometers per hour, that
Yes.
means our time must be in hours. And then when you come and get the distance, our distance will be in kilometers.
Okay.
If you have meters per minute, our time should be in minutes. And in that case, our distance will be in meters.
Okay.
Yeah,
Thanks.
you're welcome.
Good afternoon, sir.
Good afternoon to you.
So I wanted to ask, can't we use another graph of maybe displacement and the displacement and the distance, the distance and the speed? Why are we using velocity and time?
Distance and what?
The speed and distance.
Speed and distance.
Yes.
Now, why am I using a velocity time graph? Because it is easy for us to come up with for us to come up with distance using a velocity time graph. Now, when you go in for distance and time, hmm, it can still
Yes.
work. But what does it mean? You must first use the equations of motion and first find the distance that was covered in those stages.
Okay.
Are you seeing? So
Yes.
this is the best motion graph that we can give that makes our life
Okay.
so easy.
Good evening. Good afternoon,
Yes.
sir.
Good afternoon to you, Faith.
I was asking that on the graph, don't we have to
Mm.
indicate a starting point as in 0, then after we
Oh.
put that 12 there?
Aha, here you can put the 0. I had forgotten I had just forgotten that one. So you have our 0
Okay,
there. Yes, the starting point is supposed to be there. We must have a 0 there, eh?
okay, sir.
Mm. Then I'm seeing is Anita.
Yes, teacher. On that, are we going to use the acceleration?
Acceleration. Now, why have I come up with acceleration in the different stages? Eh? Because I may need to use them in the other upcoming questions. I may need
Yes.
to come up to use them in the other upcoming questions. And I want us to stick to this kind of answering, that you begin by analyzing the stages. Are you getting it? Finding the acceleration, finding the velocities, finding the time. Then you come and give the motion graph. So that in case there is a part that is requesting you to come up with a final velocity in a given stage, already you have already come up with it here in the analysis. So already have those marks got from that step. In the
Okay.
case
So
it is
then
a
do we need
part that is in the case it is a part that is requesting us to use maybe like retardation or maybe acceleration, you already got those what? Those marks.
okay. Yes.
Am
Then
I
teacher, is
clear?
there any yes. Then are we going to make any like this sketch that we have made here? Can it be the
Mm.
final or we have to put it on a graph?
This is the final diagram. This is the final
Oh,
graph. When they say a velocity time graph, you don't need to put it on the what? On the graph paper. As long as your lines are straight here, everything has been captured where the velocity is stopping, you are going to get all the marks on this graph here. Are you seeing
okay.
that my final velocity here is
Yes.
12 and here I have 12 here? Eh? My time
Yes.
here is 20 and I have 20 here. So you may not need to use the what? To use a graph paper. Just get your ruler and maybe your pen and come up with this velocity time graph. But the lines must be straight.
Yes.
Okay, okay.
Thank you.
Welcome. Danita,
Afternoon, teacher.
good afternoon to you.
Teacher, my question is, if you're given the velocity in kilometers per hour and then the
Mm.
time in minutes, is it okay
Yeah.
if you change the velocity to meters per second, then the time to seconds?
It is very, very okay. Now, the thing is here, eh? The thing is like this. If you have velocity in kilometers per hour, eh? Time has
Yes.
been given in minutes.
Mhm.
Either you change the time to hours and leave the velocity in kilometers per hour. Are you getting it? Kilometers per
Yes.
hour goes with hours. Eh?
Yes.
So then now our distance now will be in kilometers. Now, meters per second goes with seconds. So they must be coordinating. You have kilometers
Yes.
per hour. That means on the horizontal where you have time, you must have hours. Are you getting it?
Yes.
All those. Now, someone who has changed them to meters per second and then seconds here, and someone who has used kilometers per hour and let me say and hours, those people will get the same marks.
Okay.
And finally, all of you will have the same answer. The only difference is going to be that the one is going to be having the answer in meters, another is going to be having the answer in kilometers. As long as those things are coordinating, kilometers per hour, then we have hours. Then meters per second, time must be in seconds.
Yes.
So if they give you kilometers per hour, and the time was given maybe in minutes, some it was given in minutes, other time was given maybe in hours, the best way would be leave the velocity in kilometers per hour, you come and change your time here and ensure that it is in hours. Yeah.
Okay, thank you, teacher.
Because I know changing the velocity to meters per second, sometimes some people normally find challenges with that conversion. But changing time is going to be easy for you. So you can have kilometers per hour, then hours. Meters per second, then seconds.
Okay, thank you,
That is the
teacher.
must. So you can't have kilometers per hour and then you have time in seconds. It will be wrong. The shape will be correct, but the values of the distance that you will get, they will be wrong. Yeah,
Okay, thank you, teacher.
welcome. I want us to proceed. Let me answer like two people, then we can proceed to the other parts.
Excuse me, teacher.
Yes.
I am requesting for the question because I've just joined.
Now, for you, you wait for us when you're looking at the second part, or when I happen to go back. Shall go back and look at the question. So people asking about the question part, please, we shall be going back to review the other parts. I'm seeing Philip. And Philip, you're going to be the last one.
Good afternoon, teacher.
Good afternoon, Sharifa.
I was just asking that no need for the scaling.
No, there is no need for scaling, by the way. There is no need of scaling. Now, are you seeing my graph here? You see, I just come up with this, and then I come and indicate that the velocity here, corresponding to this one here, is going to be 12, and the time here is 20. There's no need of scaling.
Okay, thank you.
Welcome. Okay, let us now go on getting the distances. Now, distances here, in the first stage here, we have a triangle. So our area A1 is going to be a half times base times height. That is our area A1. Now, we come and get this area here, whereby our base is 20 from here up to here. That is our base. Our base is 20, and then our height is 12. By 2, 1, by 2, 10, I'm coming up with area A1 is giving me 120 meters. Now, you see, our time here is in seconds. So we have 20 seconds here. Our height here is in meters per second. Now, when you come to multiply here, area A1 is given by a half. Our base is 20 seconds. Our height is 12 meters per second. Now this will give us 1/2 times 20 times 12, then S times M power -1. Now, if you know very well that you covered indices in mathematics, we are multiplying. This is S power 1 here and S power -1. It will end up giving us 1. And finally, our A1 is going to be in meters. That's why here, if you're getting the area here, please don't put meters squared. You simply put meters. Because you are multiplying the time in seconds, whereas the velocity is in meters per second. So now the S on the time and the S on the meters per second, they are going to cancel out and give us 1. And our final area is going to be in meters. So we come and get area A3. Area A3 is a rectangle, whereby rectangle, the distance is from here up to where? Up to there. And this distance will be given by 420 minus 20, which will give us our area A2. Area A2 is going to be length times width. Area A2 is going to be uh, our length is 400 and our width is 12. So this is going to be 12. And my A2 is going to be 4800 meters. Though this one was already given. So there was no need of us calculating it. Now, area A3 is a rectangle which is given by base, half base times height. Our base is a half times our base, which is 80. Our height is 12. Our A3 is, this is by 2, 1 by 2. This is 40. So it will be 40 times 12, which will eventually give me 480 what? 80 meters. Now, total area is going to be A1 plus A2 plus A3, which will give me 120 plus 4800, then plus 480. And I'll come up with my A as 120 plus 4800 plus 480. I am coming up with the area as 5400 meters. Now, don't stop there. You come and say total distance is equal to 5400 what? Meters. Now, let us come and get average speed. Average speed is equal to total distance divided by time, total time. Our total distance is 500, 5,400. Total time is 500 what? Seconds. Then we say 5400 divided by 500, which is giving me average speed as 10.8 meters per second. Now we have got our total distance as 5,400 meters, and our average velocity is 10.80 meters per second. Now remember, when we go back here, the conditions for someone to participate was distance covered, minimum 5,000. Average velocity minimum 10 meters per second. We have come up with a total distance of 5,400 meters and the average velocity of 10.8 meters per second. Then you come and conclude and say the cyclist will participate in the competition since his distance of 5400 meters exceeds the required what? The required distance with an average speed of of 10.80 meters per second. Don't forget the conclusion. The conclusion is very, very important. And these conditions are given in the question initially. So that is our solution for part what? For part A. That is our solution for part A. Now let me first look at the questions. People are having questions here. I am seeing Sandra.
Yes.
Yes,
Good
Sandra.
afternoon, sir.
Good afternoon to you.
So I'm asking, like, for
Yes.
example, if sometime the distance is, yes, it exceeds, but the average speed does not. So
Now
will the
that means
person participate or not?
Now that means that we have to go back and in the what? In the condition that was given in the scenario. In case if someone meets one of the condition is able to go through, what does it mean? However much the average velocity may be below, but he has met one of the standards, he can be able to go through. That one will come from the scenario.
Okay.
Yeah. If they say the condition is he must meet all the what? The conditions. That means now if he has filled one of the conditions, he can't go through.
Okay.
Okay.
Thank you, sir.
Welcome. Any other question? You can lower the hand down, Sandra. Do you have any other question? I'm seeing God is on.
Good afternoon, teacher.
Good afternoon to you.
Teacher, I had a question earlier on when we were dealing with the velocity time graph. You said that we do not have to always use the graph paper. So I was
Yeah.
inquiring, is there a specific time where we are obliged to use the graph paper, or is just optional? It remains optional no matter what.
It is optional no matter what. It is optional. When it is a velocity time graph,
Oh.
but if it is a distance time graph, displacement time graph, you must use a graph paper. But for the case of the velocity time graph, you are free to use just a ruler and
Okay, thank you, teacher.
welcome.
Good afternoon, Master.
Good afternoon to you.
Master, I had a question with that. For example, I write the abbreviation for time and write T. Is it allowed?
What and what?
When you write the abbreviation for time, you only write T.
It is supposed to be small t. If you're using the abbreviation, you're supposed to use small t. That is a must. Because if you use capital T represents other things. It will be periodic time. So if you're using abbreviation, you must use small t. All LC, like the whole word time. And then you put the units for that time in the brackets. Is it clear?
Yes.
Yeah.
Daniela? Laptop is slow to respond to unmuting people. Okay, I am trying to unmute people here, but it is not responding very well. I am seeing Philip, you can ask. Philip?
Okay, so mine just going up. Yes. My question is that, for example, if I'm to see the way you did, is it not allowed for us to just put, for example, you just put the heading, like, for example, if you are getting the area, you put the title, and then the average title, because if you are now writing all like this, there is a AS everywhere now, it will confuse, and even
It is what?
it will confuse. No one can analyze because there is a everywhere. It's better if you put the title and then maybe you say you are getting the area average. Like,
Oh, okay. Now you see, now what I was putting here, I was just trying to abbreviate. Now I am having A1, I'm having A2, I'm having A3, but you look at the diagram we have up there. I have A1 in the first stage, I have A2 in the second stage, I have A3 in the third stage, Now this A is standing in for total area. But now you can put subtitles that average velocity, then you come and find the average velocity down. It is very okay. And remember, you have to be organized. You have to be organized also. Okay. Let us look at part B of the item. Daniela?
Thank you, sir.
You're
So
welcome.
actually, I was
Okay.
when we are labeling the horizontal line on the graph,
Mm.
right? Which range should we move on? Okay, should we have a range that we should work on? Let me say that when they give us 20, you should just subtract from the other and then put the other one. Should we
You put
follow a
what?
range, a scale? Should we follow a scale or not?
A range of what?
Let me say that the other horizontal line on the down where it shows
Mm.
the seconds. Should we
Mm.
follow a scale? Should we follow a
There is no need
scale?
of there is no need of following the scale. Now you see here, what happened is here is that you see I have 20 here. Of course, from here up to here, I have 400 seconds. So what happens is here, using common sense, the distance for 400 seconds must be bigger. So you make it a little bit bigger, and then you put 420, then you put the demarcation there. You don't need to put a scale because a scale will end up congesting the axis and looks shabby.
Okay, thank you, sir.
You don't need to put any scale. Neither you have a question, but I don't know why it has failed here. Esther?
Teacher,
Mm.
question is you talked about the other graphs that can be drawn on a graph paper. So
Yeah?
to avoid congestion, do we like just indicate the specific things that you need on the graph, or you need to
You indicate the specifics that we need on the graph. I see. I need 12 as my final velocity. 0 was the initial. The first time was 20. Then the second time was 400. If you add it to 20, it will be 420. Then you just put those ones and make sure that your line is stopping on those specific points. See? Make sure that your lines are stopping on those specific points.
I'm talking about like the other kinds of graphs that have to be drawn on a graph paper.
Now, those ones, those ones that are supposed to be on the graph paper, they must be accurate. Accurate. So
So
that
you
means
have
you must be having a scale. That in 2 centimeters, I'm having 10 seconds. Are you seeing? So as you are demarcating, you get the corresponding velocity and the corresponding time. They must be meeting at the same point.
And do you indicate everything, like all the values
Of course, now there you
on
must
each
come
and
up with
every
a very
line, or
good scale. So let me say, let us be using 2 centimeters. Are you getting it? 2 centimeters, 2 centimeters. Like the way we do it in practical. 2 centimeters, I have 10, I have 20. Doesn't you have to put all of them. If you're using a graph paper, you must put all of them.
Okay. And also, do you draw it in pen or pencil?
Now, physics, we are okay to use a pen. We are okay to use it. Actually, I recommend using a pen in physics. Anything involving in graph work, let it be practical. You must use a pen. You must use a pen to be on a safer side.
Okay.
Yeah.
Thank you.
Okay, let us look at part B. Part 1, part A is done. Now, part B, they are saying, understand the source of heat in the rims and why water is the best for cooling the bicycle after braking. Now, here, they want us to understand, where does this heat come from? Where does this heat come from? Where does it come from? And explain why water is the best for cooling the bicycle after braking. Now, this heat is coming from friction. How do we answer? We begin by identifying. Now, the source of heat here is friction. How does it come about? You explain and say that part of the kinetic energy of the car, of the bicycle, is converted into heat energy due to friction. Let us come and let me first share this one. Share this one. Now, part B. Let me even put it on a new page. Part B, the source of heat is due to friction. 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 It's due to friction where part of the kinetic energy and the energy of the bicycle is converted into heat energy while overcoming what? While overcoming friction. While overcoming friction. Water is the best for cooling. Is the best for cooling because it has a high specific heat capacity of, you can even include the value of 4,000 joules per Kelvin kilogram. Hence, it can absorb. It can absorb can absorb a lot of heat with a lower increase in its temperature. Yeah, that is going to be our response. The source of heat is due to friction, where part of the kinetic energy of the what? Of the bicycle is converted into heat energy while overcoming friction. Water is the best for cooling because it has a high specific capacity of 4,200 joules per kilogram per Kelvin. Hence, it can absorb a lot of heat with a lower increase in its temperature. I want to see, do you have any questions there on that part? I'm going to answer only 2 people. If you have a question, I'm seeing Margaret. Yes,
Master,
Margaret?
Master, I would like to
Yes.
take you back. I would like to take you back at the first part,
Yes.
Master, about describing the motions. Are we supposed, when we are describing the motion, to put the accelerations?
Now, when you're describing motions, we
Yes.
focus on 3 things. It's
Yes.
supposed to be the initial velocity, the final velocity.
Yes.
Okay. Actually, they are supposed to be, it is a velocity, time, and acceleration. Velocity, time, and acceleration. That means you must put the velocity, the
Acceleration.
initial velocity, the final velocity, the acceleration, and then the time. Though sometimes we can give someone who has given the velocities and the time and has not included the what? Acceleration.
Okay.
Yeah. If you can find acceleration, please find it and include it in your what? That is, the car started from rest and the accelerated uniformly at 4 meters per second squared to a velocity of
Yes.
12 meters per second in 5 seconds. I'm just giving an example.
Yes.
And if you're saying acceleration, please we use at. Are you
At.
seeing? At 4 meters per second squared. Are you seeing? Then if you are
Yes.
referring to time, we either use in or 4.
Okay.
Then the
And
velocity we use 2 from a velocity of 0 meters per second to 12 meters per second.
okay. Master, another question is that why in velocity time graph, this flat line, we say that it maintained a constant speed of, yet in other graphs, we say it was at rest.
Now, here, remember now, the velocity for these graphs change depending. If it is a velocity, now if we say that the car is moving with a constant velocity, what does it mean? That the car is moving with the same velocity. Are you seeing? Time is
Yes.
increasing, but the velocity is not changing because velocity must either be changing when the graph is moving upwards or moving downwards.
Downwards.
So if it is constant velocity, it has to be straight to indicate that the velocity is the same, time is changing, going on the left hand, on the right hand side. Now, if it is a distance time graph,
Yes.
when you move from home and maybe stop at the shop somewhere in the town, are you getting it?
Yes.
Distance is increasing upwards, time is increasing horizontally. Are you getting it? Now, when you
Yes.
stop somewhere, what does it mean? There will be no change in the distance. Eh? That's why it will still stay horizontal because you are still in the same place. Distance is not changed. You have only covered the distance from home to that stationary point where you have stopped. But time will be changing on horizontal. So different graphs are treated differently.
Okay.
Hmm.
Thank you.
Welcome.
The other question you said that water has a high specific heat capacity. That's why it's the best for cooling. So I was asking if there is possibly any other reason as to why, because sometimes we meet this question and they are like give reasons as to why water is the best reasons. So is there any other reason aside from that?
Though I think you are able to. Now, though we can give other reasons, like water is readily available. So that is another reason you can give. But this is the physics reason behind its application. Yes, Anna?
Thank you, teacher. So my question is, I was given a question that's related to part B of the item we are attempting right now, the part for water. But the question we were given, it was about a car where water was poured into of us. I don't remember the name of that part where the water was poured, but they stated that where the water was poured was black, and in the same question they indicated a car radiator. So they were asking what the use of the water is. So requesting on a way I'm requesting on how I should have answered the question, or like what were the key points I was supposed to include.
So now water, the importance of the water was placed in radiator to absorb heat.
Yeah, and then the radiator was black also. They
Now
indicated.
don't stop on the water that was put there to absorb heat. You must also put reason why it is there. Why water? Water was in the radiator to absorb heat because it has a high specific capacity. Therefore, it can absorb large amounts of heat while causing a very small change in its temperature. That is the first part. Now, why are car radiators painted black? Because black is a good absorber and is also a good emitter.
Okay.
Because it absorbs the heat from the engine, then it gives us that heat to the surrounding. It's good at absorbing and is also good at giving away this what? This heat.
The heat.
That's why they're always painted black.
Okay, thank you, teacher.
Welcome.
Excuse me, teacher. What if I want to explain? What if I want to explain using the boiling point of water? Because water has a high boiling point. So
now you see
how will I use that to
that
remove the
answer?
importance of the water in the car radiator?
I don't recommend you to give that answer. Reason being, water has a boiling point of 100 degrees Celsius, not so? But we have some other liquids which have a higher boiling point, but they're not being used. So the answer shouldn't be about the boiling point. The answer should be about high specific capacity. Never put the answer as boiling point. I will cancel it and we shall also cancel it because we have some other liquids that have a higher boiling point than water. For example, like mercury. Its boiling point is two-way higher than the boiling point of what? Of water. But we don't use mercury in radiators. Because mercury is a metal, what does it mean? It has a low specific, it can easily absorb heat. So the reason shouldn't be about boiling point. It can be there, but it is not, like the actual reason why water is being used. So I think that is so. The best answer should be this is because water has a high specific capacity So it can absorb large amounts of heat while causing a very small change in its temperature. Or you can even say before reaching its boiling what? Before reaching its boiling point. It can absorb large amounts of heat before reaching its boiling what? Its boiling point. But don't give the reason as boiling point. Because we have other liquids, we have other substances that have a high boiling point than that of water, but they are not being put into application in radiators.
Yes, good afternoon, teacher.
Good afternoon to you.
May I have a question? You said that water is used in car radiators, right?
Yes.
But however, there is also this green fluid that people put as the coolant in their cars. What could that be?
The green what?
There's a green fluid people put in their car in the coolant system of their cars. So
Mm.
what could that fluid be?
Yeah, I'm not certain about that. But as far as I know, if you look at most of the heating machines in the factories, most of the cars, they may happen to be having water. But we have some other coolants which are better, eh? Which may be better than water. But now we look at their availability. Are they available? That's why if you look at most of the questions here that we happen to ask you, we ask you on what you know about. We can't ask you about other liquids which you don't know. Eh? So you may be having some other liquids, but now at this level, or if you look at the how often is it applied? How often is it being used? Hmm? It may be applied in a few cars. So that's why I want us to stick on water. And even if it is other liquid that is being used here, the reason behind it is its inability to absorb heat.
Excuse me, teacher.
Yeah.
Teacher, okay. I'm thinking of an answer where you're talking about
Mm.
latent heat. Is it
Mm.
possible to phrase an answer using latent heat?
Now, latent heat cannot come into play here. Does not apply in this question here. Eh? But where can it apply? It can apply in questions like why is ice used as a coolant, as a preserving what? Substance. Are you getting it? That's when it
Yes.
can be applied. But here it cannot apply
Mm.
because it don't apply. Latent heat is the heat that is coming in when we have change of state. Change of state. So here in this question here, please don't bring it here. Is it clear?
Yes, teacher. Thank you.
Yeah. Hmm. Yes, Doreen?
Excuse me, teacher, which may
Yeah.
ask like, why is water used as a hydrochloric fluid in machines or vehicles?
Why water is used in hydrophoric machines, Nonso?
Yes,
Now, we use water
yes.
and other liquids in the hydrophoric machines because they are incompressible. They can't be compressed.
Oh, okay.
That's why they're used in those machines. That when you apply a pressure at any single point, all of it will be transmitted. None of it will be used in compressing because if it can be compressed, what does it mean? If it is applied maybe in car brakes, it may end up causing trouble. Hmm? We want that when it is being put there, it can't be compressed.
Yes.
Yeah.
Okay.
Um, um, excuse me, teacher. I'm sorry to take all of us back to part A, but I'm inquiring like about questions where they ask about deceleration. How does it apply when somewhere they say that, let's say they were moving, then the car decelerated up to somewhere, then again it accelerated. How do you show that on the graph, and how do you apply it while working out?
Okay, I have got your question. Now, what you do, for example, let me just use an example here. Like someone came from rest. Someone came from rest. I want you to pay attention here. Someone
Yeah.
came from rest and maybe attained the velocity of maybe 12 meters, not so? And
Yes.
then maybe started moving with a constant what? With a constant velocity.
Velocity.
Then from here, this person accelerates again. Are you seeing?
Yeah.
And maybe this is a
Yes.
given velocity. Let me say the velocity is 20 maybe. Then this person now decelerates maybe to a given velocity, which may be like 15 here. Are you seeing?
Yes.
Then decelerates again, accelerates again, and then you come back to what? So this is the, just you have to, so it is moving upwards, acceleration, moving downwards, deceleration, because you can decelerate it and you don't come to rest.
Yes, sir.
When you are in a car, when you reach in a jam, you have been moving very fast. When you reach in a jam, they happen to reduce the speed. Now that reducing speed now, we'll call it now deceleration. But they
Yes.
cannot stop. It reduces the speed to a given value and maybe moves with it for some time, then accelerates again, decelerates again in that kind of manner.
Yes.
So when it decelerates maybe 15 meters per second, you simply move it down and end at that velocity. Then maybe it
Down
can
it
accelerate again, accelerate again.
again.
Yeah.
Yes. But are there instances where it can go up to the negative part below the graph?
It can go there because velocity is a what? Is a vector quantity.
Yes.
Now, when it goes there, what does it mean? You have been moving forward, not so?
Yes.
Then you stop somewhere and then you start moving backward.
Yes.
And even end
Yes.
up maybe you stop somewhere and again end up reversing.
Reverse.
Yeah.
Yes.
So it is possible.
Oh, thank you, sir.
Welcome. Anna.
Teacher, my question is still about heat, but not exact. I don't know, but it's about the Okay, like the question was, explain why two thin blankets are warmer than a single thick one. Yeah, so like, what is the difference and how should I attempt it since it's also related to heat?
Explain why two thin blankets are what?
Are warmer than one thick one.
Now, what are they trying to investigate there? Now, when you have like two thin blankets, what does it mean? In between there, we have some air. And the rate of heat transfer in the air is very, very low. It's very low. So they can be thin, but because they have a layer of air in between there, they may appear to be warmer because the rate of heat transfer in air is very low. So now, as you're explaining it there, you must explain it in terms of the rate at which it is transferred in those two materials. But in between, we have air, whereby air, the rate of heat transfer in air is very, very low. That's why they may be better than the thick blanket. Okay, let us proceed and look at part B. So part C, if you go back to our question, Part C is asking us that it determine whether the rim material will not burn the tires. Determine whether the rim material will not burn the tires. Now, we go back to the question. They are saying heat capacity of the material of the tires is 210 joules per Kelvin. The temperature just before breaking was 48 degrees. Mass of the cyclist is 65 kg. Ignore the mass of the bicycle. 20% of the work done during the braking is converted into heat energy in the rims, and all is absorbed by the tires. And lastly, the rim may burn the tire if the temperature of the tire increases beyond 62 degrees Celsius. That is the part. They are saying 20% of the work done during the braking is converted into heat energy in the rims, and is also absorbed by the tires, and is also absorbed by the tires. 20% of the work done is taken into what? Into heat energy. Is taken into it. Now we come back here. Come back. Now, the initial temperature, the heat capacity C is given as 210 joules per Kelvin. The mass of the bicycle is given as 65 kg. Initial temperature theta 1, I'm going to call it what? It is given as 48 degrees. Now, final temperature, we don't know it. Theta 2, we don't know the final temperature. After braking, of course, the temperature of the tires is going to increase. From 48, it will be on a new value due to the heat that is going to be absorbed during the what? During the braking, due to friction. Remember, they have given us heat capacity. They have given us heat capacity, not specific heat capacity. Now, when you are given heat capacity, our H quantity of heat is equal to, or let me even say heat. Heat is given by heat capacity times the change in temperature, whereby our change in temperature will be given by the final, which is theta 2, minus the initial, which is theta 1, whereby theta 2 will be the new temperature of the tire after the braking, and theta 1 will be the initial temperature of the tire before the braking. But now, when you go back here, they are saying 20% of the work are done during the braking, not during the motion. During the braking is converted to heat energy in the rims, and all is absorbed by the what? By the tires. Now let us come and find work done. How do we find work done? We find work done by getting work done is equal to work done is given by force times what? Force times distance. But remember, we are looking at the distance work done during the braking phase. Work done during the braking phase. So what does it mean? Our distance D should be the distance covered during the braking. And this distance covered during the braking is during the braking is here. That is area 3, which is 480 meters. So our distance D is 480 meters. Distance covered during the braking. Now, to come up with the force that was applied during the braking, remember that force F is equal to MA, where M is the mass and A is the acceleration. But for this case here, because during the braking, that is deceleration. So it will be F is equal to MA. Our M is 65 kilograms, and our A is the retardation which we got already. Our retardation. It was given as 0.15. Now for this case, you can ignore the negative and take the positive what? The positive answer. Our A is 0.15 meters per second squared. So our F is this is going to be the retarding force during the braking, which will be 65 times 0.15. Our F is going to equal to 65 times 0.15. I am coming up with 9.75 newtons. That is the braking force. Now we come and get our work done, which is force times the distance. My F is 9.75, and the distance is given as 480. Times 480. I am coming up with work done. Work done is going to be 4680 joules. That is the work done during the braking. Work done during braking. Then now heat energy is going to be 20% of work done, which is 20 divided by 100 times 4680, which will be times 20 divided by 100. Work done, I'm getting 936 joule. This is the heat energy. Remember, our H is equal to C into theta 1, theta 2 minus theta 1. So 936C is going to equal to our C 210 into theta 2 is the final temperature after the braking, and our theta 1 is 48. We shall have our 9 divided by 210 divided by 210. I'm getting 4.46 is equal to theta 2 minus 48. So theta 2 is going to equal to 48 plus 4.46. And my theta 2 to be the final temperature is going to be 52.46 degrees Celsius. Now we come and say the tire will not burn since its temperature after braking of the 2.46 degrees is below 62 degrees for the tire to burn. Yeah. That is the tire will not burn since its temperature after braking of 2.46 degrees is below 62 degrees Celsius for the tire to burn. So I'm going to go back here. This is our last part C. Then I'm going to be looking at the questions people are asking. Let me begin with Sandra.
Yes.
Yes,
Good
Sandra.
afternoon, sir.
Good afternoon to you.
Sir, I'm asking why you ignore the negative.
The negative here, because here I'm interested in getting the scalar, the magnitude of the force.
Okay.
Yeah, you don't need to, because for us here, we are focusing on the magnitude, because the negative there is just simply showing the direction, because acceleration is a vector quantity. But if I'm getting the
Yes.
force and I'm going to get worker done is a scalar quantity. Doesn't have direction, eh?
Yes, sir.
Hmm.
Thank you, sir.
Okay, welcome. Martha,
Good afternoon.
good
Good
afternoon
afternoon,
to you.
teacher. I am lost on the part of where you put why the A is not the 10, like acceleration due to gravity.
Why I'm not what?
Why aren't you like multiplying like when you get in the force, when you're multiplying the mass times the A, the acceleration due to gravity, which is
Now,
10.
A does not mean acceleration due to gravity. Force is given by MA. Eh? Now, we only use mg if work is done against gravity. Because when a body is moving upwards or downwards, it moves with a constant acceleration, which you are calling acceleration due to gravity. But now this breaking phase here, gravity does not play part. What is playing a part is going to be the deceleration of the car. And I repeat this, please, force is equal to ma, whereby A is acceleration, not acceleration due to gravity. You only use a G if the body is moving either upwards or downwards. F is equal to ma, whereby A is the acceleration of the body. Acceleration of the body, acceleration of the body. So use G if the body is moving up or moving down.
Okay, thank you, teacher.
Welcome.
Teacher,
Yes.
I was asking why have we given us this percent?
The what?
The 20%.
I have captured it down here. I have captured it. It is here. It is here. I began by getting the worker done, total worker done during the breaking. Then I'm saying each energy, 20% of the worker done during the breaking. That's why I'm having it here. 20 divided by 100 times worker done to come up with how much was converted into heat energy. Have you seen
Okay.
it? It is captured there to
Yes,
get heat energy.
I've seen it.
Okay, okay. Yes,
Hello? Excuse me, sir.
I am listening.
And to go back to the other calculation in heat, I'm asking why didn't you include the mass, the calculation, the formula for heat?
They gave us now, I didn't use the mass because they gave us heat capacity. When they give heat capacity, quantity of heat is given by heat capacity times the change in temperature. We only use the mass if you are given specific capacity. That's why they never even gave us the mass of the tire. They gave us mass of the person, not mass of the tire. Because for this case, we look at what is absorbing heat. Have you
Thank you,
got
sir.
me?
Yes.
I'm trying to unmute element. I think this one network is disturbing her. Okay, so we don't have any other questions, so we can proceed. We can proceed. That was item 4. Element, I don't know why. I have tried to unmute you here, but the thing is not responding. It is not responding. Yes, Blessing.
Yes, good afternoon.
Good afternoon to you.
Is there a standard equation like to help us find heat energy, or where are we getting that 20 out of 100?
Now that one is coming from the question because they say that 20% of the work are done during
Like
the
a formula.
break.
Is there a formula
No, there is
that
no
we can
formula.
use to find
There's
heat
no
energy?
formula. There is no formula. You just need to interpret the question, analyze it very well, and then you use the information given to you.
Sir, okay, I'm very sorry to ask, but I wanted to request from you. Well, I'm off topic, but I wanted to request from you that if you have any notes of digital electronics, please.
Notes of digital electronics.
Yes.
Okay, I have notes. I have good notes. I'll be sharing them with Teacher Steven maybe and share them to you.
Okay, thanks.
Okay.
Good afternoon, sir.
Yes, good afternoon to you.
Sir, I'm requesting for you to show me where other equations of linear motion can be used.
To do what?
The other equations of linear motion can be used.
Can be used, eh? Oh. Actually, we can even find these distances here using the equations of motion. I think that's going to be our last part. Eh? I'm going to do that. Eh? I'm going to do that part. You can unmute. Yes,
Excuse me,
Alia.
sir. I was inquiring. Well, where do we use MC delta theta?
MC delta theta when you are given specific capacity. When you are given specific capacity, that's when you use MC delta theta. Eh?
Okay.
But now for this case, they had given us heat capacity.
Okay.
Okay. You can unmute.
Good evening.
Good evening,
sir. Sir, I was just requesting for your help on the number of heat that came in, that was in the workshop paper, the one that had hydrogen, and then the engine, and then the one that referenced. Okay, but in the workshop paper. Thank you, teacher.
Now the problem is time. I don't know. Let me first try to check for it here, and I see whether I can see it if the time can allow, because our session is supposed to be ending at 4.
Teacher,
Yes.
I was requesting if you can send me the question because I wasn't around when you were starting. I don't know where you started from. Now I'm off topic on the question you are dealing with now.
Now, I think I will share with you the questions, this question that you have just done, and it would
Yes?
enough. And I think this very presentation, it will be
Yeah.
uploaded on YouTube.
Yeah.
It will be uploaded on YouTube. You'll be able to go there and even go through again.
Okay, sir.
Okay.
Thank you, sir.
Okay, welcome. Someone has asked about the workshop paper. Now, I'm requesting that maybe next time we shall also look at more questions coming from this very area. That is in case I am given a chance to come and discuss some physics with you. So that's when I can maybe bring in the numbers that came in Waukesha. We also look at some other parts of the paper. That is physics paper 1. But for this remaining time, allow me, I wanted to help someone that asked the question that where can we apply the other equations of motion? Maybe you can do that part, and maybe we call it a what? We call it a day. Let me first answer Rebecca, then we can go to that part. Yes, Rebecca?
I'm saying, can you at least get time and we go through the Waukesha paper?
Workshop paper, eh?
Yeah.
Now,
Like
because I'm seeing people are asking questions about Waukesha. Now, what I'm going to do in our next meeting, let us now focus on Waukesha.
Okay.
That is going to be in our next meeting. We shall look at Waukesha, going through the Waukesha paper.
It's okay.
Okay, okay. Rachel?
Teacher wasn't asking me a question.
Now, you try to lower the hand, put the hand down, because I'm seeing the hand is up.
Okay. Okay.
Good afternoon, sir.
Good afternoon to you.
So, like the last page where you answering part C, I didn't get to see the conclusion. So, I'd request you to take us back there so I can see how you concluded it.
Have you seen it now?
Yes.
The tire
Thank you,
will
sir.
not burn since its temperature after braking of 52.46 degrees is below 62 degrees for the tire to burn.
Right.
Yeah. Don't forget, people, don't forget the conclusion because it carries a mark. Don't forget the conclusion because it carries a mark. Okay. So Joshua best. Is it Joshua best? Okay, now let us look at this part here. Someone was asking about applications of the equations of motion. Now you see this part here. We can find the distance covered by using the equations of motion. Now you come and say, I'm going to try to. You can find the distance covered using the equations of motion without to. Now you can come and find distance covered under the first stage by simply using the second equation of motion, which will be S is equaling to S is equal to UT plus a half at squared. Then you come and you get our S. I'm going to call it S1, whereby S1 is the distance covered during the first what? The first stage. U was 0, time was 20, plus 1 over 2. Our A we got here 0.6 times 20 squared. So my S1 is going to equal to, when you substitute in here, 0.6 divided by 2 times 20 squared, I am coming up my S1 as 120 meters. That is the distance covered under the first what? The first stage. Now, in the second stage, S is equal to 3 plus a half 80 squared, or I can even use V squared is equal to U squared plus 2AS. My V here was 12. Let me use the second equation. This one will not get it out. Let me use the second equation. Now here, my S2 is going to equal to initial velocity. If you go back here, our initial velocity is 12. Our final velocity is 12. So initial velocity is 12 times time, which we got as 400. And for this case, our A will be 0 plus 1 over 2 times 0 times 400 squared. And my S is going to equal to 4800 meters. Distance covered in the second stage. Now, in the third stage, here, V squared is equal to U squared plus 2AS. My V is 0 in the third stage. My initial velocity was 12 squared, then plus 2. My A is negative 0.15. S is not known. I'm going to call it S3. This is 0 is going to go to 144 minus 2 times 0.15, but minus, which gives me minus 0.3, S3. Then I'll come up with 0.3, S3 is going to go to 144. Divide by 0.3, divide by 0.3. My S3 is going to go to 144 divided by 0.3. I'm coming up with 480 meters. So now you see I have this one distance here, this one here, and these distances here, they are the same which you got when you use the area method. Now to come and find the total distance here, you simply come and add. Total distance is going to go to S1 plus S2 plus S3, which will be 120 plus 480 plus 4. There's another 0 here. And I will simply come up with the same distance. So you can use the equations of motion to find the distance as long as you are good with those equations of motion. But I recommend that please stick to the one that is involving in using the velocity time graph, because it is easier when you're getting the areas under the what? Under the graph. That is the easiest method. So unless I'm going to only get like 2 questions here, and then we can call it a day. In our next discussion, if I'm given a chance, we shall be talking about Wakisha, because I saw many people have questions on Wakisha. Yes, Jeremiah.
Greetings, sir.
Okay.
I was asking for the tire temperature. Is it true that it's specifically on 62 degrees
No,
Celsius?
now that is what was given in the question, that the tire will burn out if its temperature goes beyond 62. That's what was given in the question.
Okay, sir.
It was given that if it exceeds 62 degrees, it will burn.
Okay.
God is my bright star.
Yes. Good afternoon, sir.
Good afternoon to you.
Yeah, for me, I'm just trying to request that may you please scroll to the second last screen, the second last page, such that I can analyze.
You can do what?
Such that I can analyze on the second last page only.
I think this is the second, isn't it? Oh, this one.
Yeah.
Master,
Yes, Margaret. Yes.
The question is all about, can we get questions about the Newton's law apart from the first question related about the second and the third?
The second and the third, yeah. That's what I just said. Newton's law?
Yes.
Newton's laws, eh?
Yes.
Oh, we can have it. We can have very many of them. For example, like using the second law, which says
yes,
that the rate of change of momentum is equal to force. And this takes
yes.
place in the action of the applied force. That law explains why goalkeepers, when they are getting a ball, they move their hands backwards. Why are they moving backwards? To increase on the time of contact with the ball. And by increasing the time of contact with the ball, this reduces the force of impact.
Okay.
Yeah. Then the third one, for example, why do you get a pain when you hit the wall? When you box the wall? Actions and reactions are equal, but what? But opposite. So when you hit the wall, what happens? You have acted on the wall, but the wall has also reacted by giving you that what? That pain.
Okay.
It
And
is also
master,
applied in rocket propulsion when they are launching rockets in space. The
okay.
rocket is always producing large amounts of gases, which give the rocket an upward what? An upward force.
Master, and the last question is that in call this, is it collinear?
The what?
In this, for example, two cars incidentally, they get in contact.
Those are
So that
collisions. Those are collisions. We
in
look at
collision,
conservation of linear momentum.
Cat master, in collisions, if they tell you that the car was moving in southward and collided with a car moving in northward, do we consider?
Yeah, you must consider the velocities. If it is moving south, that means its velocity is negative.
Okay, that
Yeah, you must
was
look at the direction. If it is moving south, its velocity
yes.
must be negative. If it is moving upwards, its velocity is positive. If it is moving eastwards, the velocity
Okay, thank
is
you, Master.
positive. If it is moving westwards, okay, okay. Okay. We are going to end here. We are going to end here. I'm
Yes,
going to
good
wish you a
afternoon, sir.
good. Yes.
So for me, I'm asking like, would you please repeat on that part of the hydraulic, of the Pascal's principle hydraulic press?
That one was a question that came in from someone. That why are they using water? Why are they using brake fluid? Why don't they use gases? They use liquids because liquids are incompressible.
Yes.
Yeah. And it's that now when pressure is applied at any single point, it will be transmitted throughout to the what? The entire fluid.
Yes, teacher.
But just came in.
Okay, thank you, sir.
Okay. Let me wish you a very good day, people, a very good evening. Until maybe we meet again when I'm given a chance. Have a good day.